Well, so two huge chapters of the book and two huge topics of the course, with several subtopics sitting inside that, are now over. And we are in the third chapter now, dimensional synthesis of mechanisms. And this chapter is not so big, but that is not the point. The point is that in this chapter, we don't cover a lot, okay? Because now the time has changed and uh, synthesis of mechanisms uh, is not done most of the time through those methods with which the past masters of 20th century used to do. And the modern methods by which it is mostly done nowadays, I mean, if it is done at all for that matter, okay. So if you people do it, the typical choice of yours will be the modern methods, because now these modern methods exist, and so it is not necessary to go so much in detail in geometric methods. So now we go less detail in geometric methods, and the modern computational, analytical and computational methods are actually cool, in the sense that the theory and procedure of that is only a little, and that is general enough to go on applying wherever you want. We will see how it is done. But to develop the understanding of the subject and to be aware of how this field started and how classically these problems were solved, and what is the sense of the problem, it is important for you to learn a little bit of the classical geometric methods also. And even before that, we need to understand and appreciate the problem itself. Okay, so that primarily we do today. Try to appreciate the problem itself. Okay, so typical mechanism synthesis problems may arise as one, function generation, in which you are going to give one kind of input which you can do, you can give, that is one function of time you are going to give as input, which you can do easily, and as output you would expect, you would want special different kind of function of time. Okay, so in between, what you need to do, you need to work out a relationship between the input motion and output motion. So you have to work out a functional relationship between these two, which ensures that when you give your easy kind of input to the input link, then the wanted kind of function of time is generated at the output link. Okay, so this is function generation. So typically you can give input as constant speed input. So theta 2 of t you can give as a theta plus t, that is constant, or omega 2 theta plus t. Okay, omega omega 2 t plus constant, omega 2 t plus constant, omega t plus constant. That is a kind of input that you can give most easily. That is, it started from the datum point at C position, and then you are giving constant speed omega. Okay, so theta 2 would be omega t plus c, and on that side you may ask for a complicated function. Okay, so basically you have to get the mechanism to do for you theta 4 as a function of theta 2, such that theta 4 as a function of theta 2, which is a function of time that you are giving, gives you the correct value function theta 4 of time. Okay. So this is function generation. Then there is the problem of path generation. You may want one point of one link to traverse a particular curve. Okay, so just one point of a link you want to traverse on a curve. It may not be the full curve, and it may not be for the full cycle motion of the crank, but it may be that you want for a significant part of the full cycle, you want a little straight line, or for a significant part of the cycle, you want this particular segment of this particular curve. Okay, so how to put the forward mechanism or any other mechanism in which there is a link which would traverse that curve when you operate the mechanism continuously. Okay, and in every cycle through that segment it would then operate like that only. We are talking about single degree of freedom mechanisms. Okay, so this is coupler curve synthesis. And the third is motion generation. Now, for a body, you are not interested in just one point traversing something. You have a rigid body, okay, which you want in this position and orientation at some time, then in this position and orientation, and then in that position and orientation. Okay, so like this sequence of 3, 4, 5 positions and orientations, you want a rigid body to be guided through. And so you may like to put this rigid body as the coupler of your 4-bar mechanism, or one floating link of whatever 6-bar or 8-bar mechanism I am thinking of, and then work out the dimensions in such a manner that when the mechanism is operated for theta 2 value from 23 degree to theta 2 value of 75 degree, it does go through all those 5, 3, 4, 5, 6, or 7 positions. Okay, that would be great fun. Okay, so this is the problem of rigid body guidance or motion generation. Okay, so these three are primarily the three kinds of mechanism synthesis problems that you have, and there is another kind of problem which are called dead center problems. These are concerned with motion range design. That is, when the input link moves from this end to that end, the output link moves from this end to that end. Or you can say that the output link moves from this end to that end and comes back. Okay, so it's an oscillating motion. Okay, and it takes longer time to go in the forward motion and less time in return motion, and this should be the ratio. Okay, these kind of things you can get, and there are special methods to solve such problems, and they are called dead center problems because they typically design for the mechanism to operate from one dead center to another dead center. Okay, the endpoints of an oscillating link are called the dead centers. Okay, so the now this whole thing is dimensional synthesis. I told you much earlier once that mechanism synthesis has three issues. One is type synthesis, which you do not solve by making geometric constructions and or calculations or such things. These are from common sense, engineering sense, and experience on the shop and design floor. Okay. Second is the number synthesis, the kind of um, the number of links and pairs and their connections and so on, and degrees of freedom. So that we have done a little bit. So that little bit of dimensional synthesis we will do. Okay. So here we already know the type, we already know the number of links and joints, etc. And we are interested in getting their dimensions. In this also, some of them may be known because of the prescription of the task, or because we cannot determine through our methods too many of them. So some we select and others we will need to determine. Okay. So a few basic facts are there which are useful in most of these problems, and they are important for both graphical methods and analytical methods. They are what will fix the problem for you either for the geometric arena or for the computational arena. So let us try to understand that first in proper detail through the problem of function generation, and then we will see, because in function generation that whole thing fits best, and then that same thing we will try to see how we can port path generation and motion generation problems also in this framework. Okay. So suppose we want to generate a function y equal to fx from this initial value to this final value. Okay. So for this value of x, there is a value of y. For this value of x, there is another y. So call them as y of I and y of yi and yf, y initial, y final. Then you need to define the scales. These are things that is actually part of the design, part of the synthesis. That is, with what scale theta 2 motion is to represent the function change in x. So that is delta theta 2 by delta x. That is the scale of the independent coordinate, independent variable of the function, and that is this. Okay. So this is one thing. Similarly, the scale of y. So you can say xi you want here. So you can say either I have to work out initial theta and a few other thetas after that, initial theta and the subsequent thetas, or you can, and which will ensure the final theta also. Okay. Okay. No. Yeah. You can say either I have to find out initial theta and final theta, or I have to find out the initial theta and the scale. Okay. Because xi and xf are given. So in this equation there are three other things. One is initial theta 2, final theta 2, and rx. So two of them you have to basically design. The third gets determined. If you design these two, then rx gets determined. If you design this and this, then this gets defined. Okay, through this. Fine. So that means the choice of the scale for the independent variable of the function needs to talk about two things to be determined, and here another two things. So these four are the design parameters. These. Okay. Or alternatively, you could have said theta 2i, theta 2f, theta 4i, theta 4f. So these four, and then the actual mechanism dimension related parameters. Now, for a four-bar mechanism, four quantities L1, L2, L3, L4 are not important. Because for this, we are talking only of rotational quantities. So whether the mechanism links are in centimeters or in meters, it will not matter. Okay. So it is the ratios which will govern everything. Okay. So L1 by L2, L1 by L3, L1 by L4. You could have put any one of them common, any three proper independent ratios you could have taken. So there are 7 parameters, 7 design parameters. If you have designed these 7 things, found out first class values for these 7 quantities, then you have done a great job in synthesis of a 4-bar mechanism for function generation. Okay. If the mechanism is more complicated, 6-bar, 8-bar, or whatever, then there will be more parameters from here. Okay, and that will make the problem more complicated. And geometric methods are mostly within the scope of 4-bar mechanisms, which is versatile enough for that matter, because 4-bar mechanisms can give you a lot of kinds of things. Okay, now the point is how to do this. Uh-oh. Yeah. So you can say fx is the function that I wanted. Now these 7 parameters, call them R1, R2, R3, R4, whatever, up to Rk. K may be 3, 4, 5, 6, 7 or more for whatever reason. Okay. So if we choose some values from our head, okay, for R1, R2, R3, etc., and then assemble the mechanism and start running it, then what will happen? As a function of x, this whole thing will produce some function. Perhaps that will not be y. Okay, it will be something else. But whatever is that, let us call that capital F. So f of x is what we wanted, and capital F, depending upon x and these things, these are the parameters which define the function, and x is the argument of the function. So capital F we would get. Now, whatever is the difference between the two, that would define the error function. Okay, and now the way to design it may be to reduce the error or make the error 0. Now, where a function has in its domain infinite points, okay, infinite values of x continuously. You say that if we could match the requirement with what we get at a number of values of x, then we say more or less whatever we wanted, that is what we have got. Okay, so that is typical process, whether you do it geometrically, analytically, computationally, whatever, that is fine. Okay, so how do we match these to several points? You say select several points, then the question arises, for which values of x we try to settle this. Okay, and in that there is a beautiful background work from Chebyshev, and this is what we discuss in proper seriousness. Okay, so you study this page for 1 minute, perhaps by stopping the video here, and I will join you back after 1 minute for you and perhaps 5 minutes for me. Okay. So Chebyshev approximation theory or minimax approximation theory uh, helps a lot in settling this question. And so to answer this, how to select design parameters R1, R2, etc. up to Rk such that the maximum value of the error function is minimized over the domain. Actually, this question is loaded. This question is the most important thing, because if you are trying to approximate a function, then how do we approximate it if we expect the function to be evaluated at every point? Okay, so to match the function to the requirement precisely at some point and very badly at some other point will be very bad, right? So you would like to have an approximation which matches the requirement in such a manner that the deviation, the maximum deviation over the domain is minimized. So if at one point it is high, at another point it is low, then you try to make some changes in the design parameters so that the high becomes a little lower, the lower become a little higher, maybe okay, part of the deal, what to do about it. So you will tolerate it, because anyway that much deviation is taking place somewhere else. What about creating so much fuss about this little one? Okay, so that is the topic of minimax approximation. Minimax approximation, which is also called Chebyshev approximation, is actually a very powerful and extremely interesting topic in approximation theory. And I advise you to go through it sometime. It's pure intellectual pleasure. Actually, I have one lecture in YouTube on that. So anyway, so the ideal solution would be try to make the error function oscillate among alternate k plus 1 extrema of opposite signs and equal magnitude over the entire interval, like this. The deviation, if you are going to fix 5 parameters R1 to R5, then it would be the best to do it in such a way that the error or the deviation changes from the starting of the domain to the end of the domain in this manner, that it has 6 extrema: one maximum, one minimum, one maximum, one minimum, one maximum, one minimum. Okay, so alternate signs. So if the maximum deviation is plus epsilon, the minimum deviation should be minus epsilon, and all these three maxima should be the same, plus epsilon, and all these three minima should be the same, minus epsilon. If you have managed like this, that means that there is nothing better you can do with just 5 parameters in hand. Okay, so this result is actually a very important result in approximation theory. So a very good approach for this is to design the error function as a linear combination of the so-called Chebyshev polynomials. Okay, because each Chebyshev polynomial has a property of this kind. Okay, so the first one stays. First one is constant, that is 0, t0. Second one is a linear function running from minus epsilon to epsilon. The third one is a quadratic function running from 1 down to minus 1 and then again 1. Cubic one, that is the third one, that is T3, changes from minus 1 to plus 1 to minus 1 to plus 1. Okay, 3 rounds. which means 4 extrema, and so on. So this needs you to design the error function by using the Chebyshev polynomials as basis functions. Okay, alpha 0 times this plus alpha 1 times this, and so on till this. So now, if you try to do it exactly as it has been said here, then it will be a little longer route. A shorter route to do the same thing has been found as Chebyshev-Lagrange approximation. Okay, what you do for that? For that, you take the kth Chebyshev polynomial, which is Tk, which is of degree k, and therefore has k roots. Okay, so you find the k roots of these. These are found and kept. These are there. Okay, and call them Chebyshev accuracy points. And then the claim is that if you can manage to make the designed function match exactly at these values of x, then that will be the best that you can achieve with k parameters in hand. So then what you do is that in order to get this polynomial function, you can do simply the ordinary Lagrange approximation, Lagrange interpolation of function values at those x values. Okay, so at these points match the function exactly, error 0, and then through these points simply do an ordinary Lagrange interpolation that will give you exactly this. Now each of these steps has been established mathematically, and they are of great value in approximation theory. Okay, in minimax theorem, minimax approximation. Okay, now this one, to do this, I mean, doing this as it is written here in these 4 lines is actually not very difficult, because roots of tkx are known. Okay, and doing this is quite straightforward. However, you have to rescale the variable x from -1 to 1, from whatever xi to xf you have. But then doing this rescaling of the independent variable and doing the actual thing, both of those things you can do together through this interesting, beautiful construction. How to determine Chebyshev accuracy points. Okay, so Chebyshev functions are basically this. Okay, so tkx is for x running from -1 to 1, it is cosine of k times cos inverse x. Okay. So it turns out to be a polynomial actually. That is very interesting. If you take theta as cos inverse x and put k theta here, okay, then you evaluate cos k theta. So cos k theta will turn out to be a polynomial of cos theta. That is polynomial of x. That is very interesting. So Chebyshev polynomial is at the same time a cosine function as well as a polynomial function. That's a very enviable combination of interesting properties. So practical way to find out k Chebyshev accuracy points in your required interval. Okay, equivalently roots of this for a scaled x bar over this. You draw a semicircle over this interval. So you see, this is xi, this is xf. So on this line segment, you draw a semicircle. Okay. Actually, this does the rescaling job. Okay, and then divide this semicircle into 2k equal arcs. So here I have shown you the example of k equal to 3. Okay. So 2k will be 6. So 6 parts, each of 30 degrees. Fine. And then these points you just project on the ground, the odd ones, not the zeroth one. The first one you project, get one accuracy point. The second one you leave out. The third one you project, you get the second accuracy point. And then the fifth one you project and you get the third accuracy point. That's it. So by projecting, you are actually doing this cosine. Okay. So abscissas of odd marks will be your Chebyshev accuracy points. Okay. Actually, because the Chebyshev polynomial of the third degree has this graph. Okay. It starts from -1 at x equal to -1, runs to this, which is basically minus half, and then plus half, plus half, plus half x equal to plus half. Here the maximum value of fx equal to minus t3x equal to plus 1 comes. So -1 at -1, plus 1 at minus half, and then minus half at plus half, and finally 1 again at x equal to 1. Okay. In between the and at the extreme, this one, this one, this one, and this one give you the extrema. Okay, these are the extrema we were talking about. In between these ones, this one is the 0. Okay, here the Chebyshev polynomial cuts the x-axis, and if you put the error like this, which passes through this point, and this point, that means at these 3 points you are making the error 0. Okay. So in these 3 points, at these 3 points, you will try to match the function exactly. If k equal to 3, you will get 3 such points. If k equal to 4, you would get 4 such points, and so on. And now the point is that in between, the error function everywhere will not follow this. Okay, but then it will be as good as possible, as close to this as possible through 3 parameters. And if you then want to make some small modifications, then you can try it out based on the original minimax principle, which is this. Starting from that as the first possibility, you try to make it like this. Okay, so that all the 4 maxima are really of the correct magnitude and alternate signs. Okay, so right now you are ensuring only 0. And there is a beautiful algorithm to accomplish that from a starting solution iteratively. But even without that iterative process, the solution that you will get from this is reasonably good. Now we need to, have we finished it? Yes. Now we have decided to fix the function value at these few points and then do the synthesis, either geometrically or computationally. But before that, before proceeding with those methods of this kind or that kind, let us see how we convert a path generation problem or motion generation problem into that framework, in this basic synthesis framework. So suppose it's a path generation problem. So what is the problem? Problem is you want a mechanism like this, in which on a floating link for a 4 bar, there is only one floating link, which is a coupler. So on that coupler, you need to select a point. So selection of the mechanism parameters, then selection of coupler point, and selection of interval of theta2, interval of the input motion, that is from this angle to this angle of the input link. You want this curve or this segment of a larger curve perhaps to be traversed by this particular point of the coupler. And now you have to design which particular point of the coupler, and for that matter the geometry of the coupler, geometry of this, relative geometry of everything. Okay, so this is the task. All of these you cannot synthesize, some of these you select, otherwise you don't get even a reference to do the rest of it, and then the rest of it you have to design. Now how do we put it in the Chebyshev framework? So we can cast this into the Chebyshev formalism by defining an error function. So we define the curve that a point P actually generates if we give hand-picked values of the kinematic parameters, dimensional parameters of the mechanism, and we give hand-picked location of P. Then this point P will generate some curve for that interval of theta 2. Whatever is that curve, theta 2, theta 2, theta 2, theta 2 values for different values of theta 2, we take there its difference from the curve commanded. Okay, Euclidean distance. Okay, wherever our designed mechanism gives puts P at theta 2 equal to 32 degree, and wherever at 32 degree it was wanted. Okay, difference of that, and that difference over all the entire domain is the difference function. Okay, so through that define the error function based on the deviation of the generated curve from the demanded curve, and based on this error function then decide the accuracy points as you did for function generation. How do you do it for motion generation problem? This is not even this simple. What you do, for example, what is the problem here? In motion generation problem, you have to guide a rigid body through specified positions and orientations. Okay, so say first position, second position, and third position. Actually you want through infinite positions, you want actually a continuous guidance over a series of configurations for the body. Now it is not a single point, it is one point and an orientation. Okay, so you can parameterize this in the form of x of u, y of u, theta of u. U is a parameter. Okay, so wherever a particular point of the body is for a value of the input angle theta 2. Okay, so call it x, the y, so that is the coordinates, and then one line you have selected. So wherever that line cuts, you take the theta angle. So this x, y, theta as a function of some parameter. Okay, u. You put it like this. Okay, and then this is a vector function. After you have parameterized this, you say that this is the vector function that we want. Okay, and the problem has directly been put in the function generation arena, except that here there are quite a few scalar functions that it's a vector function. But then error you can work out. Okay, error in x and error in y and error in theta together you put as error at this particular configuration. Okay, I mean either you take a Euclidean norm or you weight the theta a little differently. I mean that is up to your policy. You know the scaling of your problem. So based on that, you can decide the accuracy points. Okay, so this is the definition of the framework of the problem through the Chebyshev spacing formalism. Now we have a crossroad where we can go in the geometric way or in the analytical way. From this point onwards, one can go either way. That means we who want to go both ways can take up any of the two first and the other later. So we will take up the geometric methods first, and the more powerful, more general, more versatile method of analytical and computational techniques we will take up later. Okay, so here we are done with the problem definition.